Okay, so we have one more example involving related rates for Math 1560, Calc 1 at U of L for fall 2017. And this one is the third example on that introductory video that we looked at. Okay, so this time we've got to spend a little bit more time on our diagram. So we've got a lighthouse with a revolving light, and that lighthouse is out in, I guess, the ocean, let's say, away from a straight shoreline. So what we do here is we draw our shoreline, and out here, here's our lighthouse, okay? And now we start putting in information. So the distance from the lighthouse to the shore, so distance is always measured as perpendicular distance. That distance is 500 meters. And we want to know how fast is that light traveling. So the beam of light, and then we're going to assume that the beam of light doesn't expand too much, right? So there's a beam of light coming out from the lighthouse, and it lands at some point on the shore here, okay? And we want to know how fast the light is traveling along the shore at the instant that it's 1 kilometer from the point closest to the lighthouse. So what we're interested in here is we're interested in the rate at which this distance is changing. That's going to give me the speed that point is moving along the shore. So let's label that x. Okay, that's our distance. Alright, but right now we only have one variable, right? What's our other variable going to be? What's the other information that we're given? 1 revolution per minute. Revolutions per minute, what kind of quantities are involved there, right? Here's where you have to really think about this. Not everything is always spelled out for you. What is changing when you're dealing with revolutions? What's changing is an angle. What's the angle in this case? This one here. There's an angle theta, right? That angle is changing at a constant rate. We know what that rate is. Alright, now what's our relationship between the variables? Well, I've got an angle. I've labeled the opposite side. It's a variable. I know the adjacent side. That's constant. It's 500. And so what do I know? I know that tan theta is equal to x over 500. Okay, that's the relationship between my variables. Okay, and if I want, since x is the thing I'm interested in, I can actually solve for x here. X is equal to 500 tan theta. And now I want the rate at which x is changing, so I need to take the derivative of both sides with respect to t, dx dt, 500. So I do the derivative of tan. So remember, the derivative of tan theta is secant squared theta. But then I'm taking the derivative with respect to t, so I need to multiply by d theta dt. Alright, now, when x is equal to 1, okay, I know that tan theta is 1 over, and now we have to be a little bit careful, right? Here's one of these reading issues. 500 tan theta, is that really what I want? Units, guys. Meters, kilometers. How many meters in a kilometer? 1,000 meters in a kilometer. So let's say I choose to work in, what do we want to work in? Do we want to work in meters? Leave that as 500. Let's do it that way. So really, what we mean here is not x equals 1, but when x equals 1,000. So 1,000 over 500, which is 2. Okay, and so let me draw a little triangle, 2, 1. Things are not to scale here. This side is square root of 5. So secant theta is going to be adjacent, or sorry, hypotenuse over adjacent, root 5 over 1. So secant squared, just 5. Okay, so what do we get? We get, so 500 times secant squared times, And now we have to be a little bit more careful. 1 revolution per minute is how many radians per minute. Remember that we are working in radians. Angles are always measured in radians for calculus problems. Otherwise, none of those derivative formulas are correct. So how many radians in 1 revolution? Well, 2 pi. That's a full revolution, right? So this is 2 pi radians per minute. Okay, so we put that in. 2 pi. Okay, so overall what do we have? We've got 500 times 5 to 2500 times 2. That's 5000 pi, and that's going to be in meters. We got to make sure we get our units right. We did everything in meters, right? So meters per minute. Or if you want to, I guess we could put that back into kilometers. 5 pi kilometers per minute. And that does it for this one. Okay. We'll do a few more examples in class, and then we're going to move on to optimization.